Okay, now this is the last part of the ADC converter. Today I want to teach you that is the dual slope type AD converter. Today in the previous class we learned the counter type ADC and the flash type ADC. So as similar of the counter type ADC, in the dual slope ADC have the extra components like the integrator, one flip-flop, one latches, and as similar as the comparator and the in-bit up counter and the AND gate. So why it is called dual slope? Because there is a two slope. One is the negative slope and the positive slope. When the input switch is connected to the positive input voltage of the integrated input, then the output of this integrator produces the negative ramp, negative slope ramp voltage. And when the input switch is connected to the minus VR of this integrator, then the integrator produces the positive ramp. So here this is the negative ramp, here this is the positive ramp, or there is two slope, one is the negative slope and another is the positive slope. So for this reason it is called the dual slope. In the dual slope type ADC, the integrator generates the two different ramps, one with the unknown analog input voltage V in as the input, and another with a known reference voltage that is called minus VR as the input. Hence it is called the dual slope. The mechanical switch connected at the input, this is the mechanical switch of the integrator, which is controlled by the output of the T flip-flop. When the output of the T flip-flop is logic 1, then the switch is connected to B in, and when it is logic 0, then the switch is connected to minus VR. First assume that the initial output of the T flip-flop is logic 1. That means the input of the integrator is connected to the analog input signal B in, as shown in the figure. T flip-flop is nothing but a negative edge trigger flip-flop, and it is triggered according to the negative edge of the MSB of the n-bit up counter. Here it is shown as the Bn-1. In the other words, the output of the T flip-flop will not change until the Bn-1 changes from 1 to 0. Okay. The n-bit counter is clocked according to the clock signal and the output of the comparator VC. When the V1 is greater than 0, then the VC will be 0, as the comparator is the inverting comparator. So if it is greater than 0, that means positive 1, positive voltage 1, then the output will be 0. When the V1 is less than 0, then it is negative, then the output of the inverting comparator will be at logic 1. So we can get this is the VC of the comparator output. Assume that the n-bit up counter is initially reset. So the 4-digit decade counter is initially reset to 0. The ramp output V1 is reset to 0 volt. Analog input voltage is positive. and the input to the ramp generator or the integrator is switched to the unknown analog input voltage. Since the positive analog input voltage is connected to the inverting input of the integrator, the integrator output V1 is a negative ramp due to the inverting integrator. So the comparator output VC is obviously the positive. Here this is negative. So that means due to the inverting comparator, the VC should be positive. So as VC should be positive, it treated as a logic 1. If this is logic 1, then the clock is passed through the AND gate. And this results in counting the up counter, the 4-digit decade counter. Initial condition at t is equal to 0. The Q is equal to 1 at initial stage. So the switch is connected to the V. So the output of the integrator is V1t is equal to minus 1 by RC 0 to 2 V in dt. So that's equal to minus 1 by RC V in t, where R and C are the time constant of the ramp generator circuit, like integrator. So if the input voltage is positive, then the output of the integrator is negative. Or V1 less than 0. So the VC is equal to 1. As VC is equal to 1, now the n-bit up counter will count in the up direction. The moment V1 tends to go below 0, the clock pulses reach the clock input terminal of the counter, which is initially cleared to all zeros. First, initially it is cleared to all zeros. So the counter will start counting from 0, 0, 0, 0 to 1, 1, 1, 1. So this process will continue for the 2 to the power of n clock cycles. And the 2 to the power of n clock cycle output of the counter is the final count, that is called 1, 1, 1, 1. All 1. So at the 2 to the power of n clock pulse, the counter is again clear. Why? Because this is all are 1. All are 1. So then all are 1. This is the 1 to 0 clock pulse. So the counter is again clear, then the 1 to 0 transition will occur. If the 1 to 0 transition of the MSB bit of the counter, that is Bn-1, occur, then the counter sets the flip-flop. That means the S is now connect to the integrator input to a reference voltage of the polarity, opposite polarity of the Vin, that is minus Vr, because Q is equal to 0. If it is 1 to 0 transition occur, then the T flip-flop is set. So the input is 1 is transferred to 0 output. So the output of the T will be 0. So due to the Q is 0, then the switch is also connected to minus Br. So this is the logical operation. Now in mathematics, at the time T is equal to T1, at that point, where the T1 is the 2 to the power of n into Tc time. Tc is the clock period of the clock pulses, and a 2 to the power of n number of clock pulses are there. So the total time T1 is equal to 2 to the power of n into Tc. So if I put T is equal to T1 is equal to 2 to the power of n Tc, then we will get V1 T is equal to minus 1 by RC V in into T. That means T to the power of n into Tc. In the next clock output of the n bit up counter is all 0. This will trigger the T flip-flop, and the output of the T flip-flop will change to 0, which is already said in the previous paragraph. It means the input of the integrator is now connected to minus BR. This is the mathematical expression of this statement. Now the ramp integrator begins at minus V1 and increase upward until it rises to the 0. So minus V1 RC by T, RC into T1, that means minus V in by RC into V to the power of NTC. It will start from the 0. Sorry, it will start from the minus V in by RC into T1 to 0 at the time of T2. So during this time, the counter gets advanced. So when the V1 reaches to 0, the comparator output will become 0. V1 reaches to 0, then the comparator output will become 0. So the clock is inhibited from the passing through the AND gate. So there is no clock. Okay. So then it is stop counting. So when T is greater than 2 to the power of NTC, just greater than T1, then what happens? Now it is connected to minus BR. So minus 1 by RC integrate to minus BR dt. So that is BR by RC into T plus K. Where the T is equal to 2 to the power NTC, V1 T is equal to minus 1 by RC into B into T again. So if we compare these two equations like this, then we will get the value of K. Now put the value of K in this equation. Then we will get V1 T is equal to VR by RC into T minus 2 to the power of NTC by RC into V in plus VR. So V1 T is equal to VR by RC T minus 2 to the power of NTC minus 2 to the power of NTC by RC into V. Assuming that 2 to the power of NTC is equal to T1. So now we put 2 to the power of NTC is equal to T1. So then we will get VR by RC T minus T1 minus V in by RC into T1. For T greater than T1, the output of the integrator is negative. And its value is increasing. Due to this, output of the comparator will be 1. Then the up counter will count in up direction. This process will continue until the output of the integrator becomes 0 after the n number of clock cycles, capital N number of clock cycles. So at the time of T2, the V1 T is equal to 0. At the time of T2, the V1 T equal to 0. So if we put 0 is equal to VR by RC into T2 minus T1 from this equation, then we will get this. So now we will get this and put this T2 minus T1 is equal to N into TC. This is the total time T2. This is the total time T1. So this is called the T2 minus T1. T2 minus T1. So then we will get NTC. So the N is equal to V in by VR into 2 to the power of N. Here we can see that the V in VR is constant, we know. 2 to the power of N is already known. So the N is directly proportional to the input voltage V. What is N? The N is the binary equivalent of the digital output. Binary equivalent of the digital output. So the output of the ADC, dual slope ADC, is directly proportional to the input voltage. So we can see that V in is equal to VR into T2 minus T1 by T1 also. So from the above equation, it is clear that the unknown analog input voltage is proportional to the time period T2 because VR is known reference voltage and T1 is the predetermined time period. Also, the contents of the 4-digit decade counters at the end of conversion reflect the variable time period T2. The conversion time 2 to the power of NTC plus N into TC. This is the 2 to the power of NTC plus N into TC. So this is the total conversion time. Okay. So this is the total conversion time. This is for T1, this is for T2, T2 minus T1. So then we will get this. So this is very much important for the gate examination. The total conversion time of the dual slope AD converter. So in conclusion is that when the switch is connected to V in, then the V1 is negative, less than 0. So the VC will be 1. As the VC will be 1, then the clock pulse will be ended to, and it is as the clock pulse of the counter, then the counter will start counting. Firstly, the counter is initially reset to 0. So the counter will start counting from 0 to 0002 in increasing manner as a up counter. Now, this T flip-flop can be operated with respect to the MSB bit of the output of the N bit counter, that is Bn minus 1. When the Bn minus 1 will not be changed from 1 to 0, then the output of the T flip-flop will not be changed. So at the first time, we assume that Q is equal to 1. For this reason, it is connected with the V in. Now, when this is all of the ones at the time of T1, then what happens? It will be starts counting as 0. It is converted from 1 1 1 1 to 0 0 0 0. So the 1 to 0 transition will occur, and due to this 1 to 0 transition, the T flip-flop will be in set position. So the Q will be 0 due to the input voltage is 1 here. So when the Q is 0, then the switch is connected to the minus VR, and the output of the integrator is minus into minus, that means plus, so it is greater than 0. So then the VC will be again 0. Okay. So if this is not 0, if this is 0, then what happens? So the counter is not counting. So it stopped counting. That is the 0 0 0 1 1 1 1 and 2 0 0 0. Now if this voltage is at the time of T1 to T2, at the time of 2 to the power of N into TC, then it is happens from the minus B1 RC T1 to 0. When it is 0, the output of the integrator will be in 0, then BC will be again 1, and then again it will be counting from 0, 0, 0 to 1, 1, 1, 1 for the minus BR, and the slope will be in positive, and the mathematical expressions will be described accordingly. So this is the basic principle of the dual slope AD converter, and this is the conversion time. This is the V in at the time of T2 and T1, and this is the at the time of T2, where we will get the N is equal to the binary equivalent binary digital output, which is proportional to the directly proportional to the V in. And at the time of T1, that is 2 to the power of NTC, we will get V1 is equal to like this. And when it is greater than 2 to the power of NTC or greater than T2, then we will get V1 is equal to like this. The value of R is calculated by this expression, and we will get the final value as like this. Okay, so at the time of T2 and at the time of T1, the value of V1 will be calculated. And according to the V1, the VC will be set 1 or 0. When it is 1, then the counter will start counting. When it is not 1, it is 0, then the counter will stop counting after completing the 2 to the power of n pulses as 1, 1, 1, 1. So this is the basic principle of the dual slope AD converter. Thank you.